All right, so here we're going to go through the first of what'll amount to be 5 videos, one for each portion or each unit on the final exam review packet. So we're going to be starting here with Unit 1, our Chemistry Fundamentals unit, and you have kind of the topics that were covered across the entirety of that unit. That was our introductory unit. So the first thing that we're going to talk about is the differences between physical and chemical changes. The 3 signs, and again, there were more like 5 signs, so I'll put them all here, of a chemical change. Well, one thing that we know about a chemical change is that it is irreversible, which means that once it happens, we more often than not can't get whatever we started with back, right? So that was one way that we were able to identify it, but a way that you can identify specifically how that works would be a sudden color change. Another one could be sudden gain or loss of heat, right? So sudden temperature change effectively is what that is, and it's something that you're not physically doing, like boiling a pot of water. You're physically changing that the amount of heat, but if it just happens spontaneously, and I'll add that irreversible, spontaneous, which means again, the word sudden, all right? Spontaneous. Another sign would be a sudden odor, all right? Something that was not there beforehand. We talked about bubbles or effervescence, which is the production of gas. So gas production, gas that was not there before and then all of a sudden is. And then we can also just say the ability to have a precipitate, or, and I'll just say slash solid form. Like if we mix 2 aqueous solutions and all of a sudden we get a solid that is also a different color or something like that, that would constitute a chemical change there as well. So again, chemical change is something new. All right, that was the big thing. It is something new, something that has a new chemical identity based on the way that those elements are now bonding together, or not bonding together, right? Some major difference between physical and chemical changes. If chemical changes are irreversible and spontaneous, then we could say that a physical change leads us to have a something that is reversible, no new chemical composition. Again, that's the identity. So no new chemical composition, same thing. So a lot of times the examples for this is our phase changes, right? Going from liquid to solid, solid to gas, all of those types of changes, and the actual the appearance changes in physical changes very similar to our chemical changes, but the major thing to remember is that there is nothing new changing, where there was new, or I should say different chemical composition. So the identity of the chemical formulas and the elements that are bonding together are different. So different chemical composition. That tells you something new is being formed, something that wasn't there prior. Then we talked about our vocab, element compound mixture. An easy way to talk about elements and compounds was that elements are found on our periodic table of elements, correct? And each symbol which begins with a capital letter and has a maximum of 2 letters, right? If there are 2 letters, right, there is going to be a capital and a lowercase right after it. That effectively, anytime we see just one capital letter in a chemical formula, we know that we are just dealing with one element. Now, because we have this 2 here, that is 2 oxygen that are bonded together. So it is still oxygen, right? The element by itself. But because oxygen's a diatomic, we had mentioned that it would bond to another oxygen in order to completely be stable. So we say that those diatomics they are in need of being paired with something. And so if it's by itself, then it would be just one. If it's by itself, then it would be partnered up with itself, another one like it. And one other thing we said was that now any grouping we could consider to be a molecule. So we can have a molecule in terms of those things coming together. And then if you look at our next one, I'll delete that. Our next one, we see that we have 2 elements that are also together, but the difference here is that there are 2 different elements, and 2 different elements would mean that we have a compound, right? 2 or more different elements chemically bonded together. And so this would be a sodium with a chlorine, and we see that that's also a grouping. So by our definition, we could consider that to be a molecule. It's really a formula unit because it's ionic, but we say any grouping we can consider a molecule because it's more than one atom. So we can have something be an element and a molecule. We can have something be a compound and a molecule. But it depends on what the identity of that is that determines whether or not it is an element or a compound. In this one, we just see copper right there. It's 1 capital letter, 1 symbol, so that is just an element. And then the big giveaway for mixtures, when we take things and we just dump them in physically with one another, and they don't change chemically, they don't change and form something new, we just call it a mixture. We, of course, have homogeneous mixtures and heterogeneous mixtures, which does everything look the same, or does it like Gatorade or something like that, a lot of solution? Or does it look different? Can I physically see the difference? And those are heterogeneous, right? Like vegetable soup, so on and so forth. We can also look at our particle pictures to identify what these are. We have compound here. It is not a mixture, even though there's multiple different shapes. Each shape represents its own element. So this is what we would call element circle. This would be what we call element rectangle. But because they are together, they're bonded, that's what the picture is showing, that is what makes it a compound. And everything in here is all the same. So again, compounds, when they are only with others alike, then it is considered to be a pure substance. Just like this element over here, we see that there's only one shape. It is element circle, correct? So we have just that. This is, again, another pure substance. So our pure substances are just things that are in the same sample that are not different from one another. So that's a pure substance there. And then, of course, here we have a mixture, and that's because there are a bunch of different shapes. I mean, right, we have element circle here. We have element triangle. We have element rectangle that's bonded to an element circle. Right? A bunch of different things that are not exactly alike and exactly replicating one another. So that is why this would be considered a mixture there. Then we got into scientific notation. This was really helpful when we got into the mole concept, where we were talking about Avogadro's number and how large it is in terms of 602 sextillion, which is a crazy big number. So it's a lot easier to represent that in scientific notation, because in scientific notation, you always start with a decimal after the first non-zero number within the number itself. So when I see this first one for A, the first non-zero number I see is 2, so my decimal is going to go after 2 if I want to change this into scientific notation. And then I tack on whatever other numbers I have to the right of it based on if when I see my last non-zero number. So in this case, it's just 4. If there were zeros past it, I would also include those. I don't have to include the ones prior. And then we have to multiply this by some factor of 10 based on where does this decimal move in order to end up where it is in the actual standard notation. And so what I like to do is I like to say, well, based on scientific notation, if we know that a decimal has to be after the first non-zero number, then let's place it there, and then let's just see what direction we have to move in order to get to the end of our number. And in this case, the end is this decimal right here. And so in order to get to this point, we would have to move this decimal to the left, which tells us that this is going to be multiplied by a factor of 10, but negative, right? There's going to be a negative exponent, and that exponent here is just how many times we have to move that decimal. And so we go 1, 2, 3, 4, 5, 6, 7, and 8. That's how we know this is 2.4 times 10 to the negative 8 if we wanted to rewrite that. We do the same thing in the other direction as well, like in B. Now this is not a decimal, that is just the letter B, right, for the the question numbering there. But in this case, for scientific notation, remember, we want to identify the first non-zero number that we see. The first non-zero number that we see is actually this 1. So I'm going to put the decimal to the right of that when I start scientific notation. And then I notice that there are zeros here, but they're sandwiched in between 2 other non-zero numbers, which means that I'm going to have to include every number that I see there up until the 3. So this is 1.0073. All right, but we still do this the same way as we did the other, and we have to multiply by some factor of 10, and then we say, okay, well, if I had a decimal here, right after the 1, which direction would I have to move in order to get to the end of my number? And I say I have to move it this way, to the right. And we know that conventionally the right is the positive direction, which means that this would end up being moved to the right 1, 2, 3, 4 times, which is why the exponent here is positive, and it's positive 4. All right, we move to the right 4 times. All right, by that same logic, usually you wouldn't have a number this small in scientific notation, but we're going to do it anyway. Here's 5. Is my first non-zero number, so I'm going to start with 5.6, and because this 0 is included, that means it's significant to us, so we want to just include it with the 6 there. That just means that the level of precision is a little bit greater there. And then we identify, okay, well, in order to get to where that decimal ends up, what direction would I have to move it away from this 5, to the right or to the left? And we notice that we have to move it to the right, which means we're going to have a positive exponent there. And then how many times did we move it? Well, honestly, we just moved it 1 space. So realistically, this is just 10 to the first, or we're multiplying this number 5.60 by just 10 by itself. That's why this one's kind of silly, but again, it gets the idea of which direction you need to move the decimal and what that means for scientific notation. For letter D here, the first non-zero number I see is 8, so I'm going to put 8 and then 0.09. Now, before we included the 0 after. In this case, we don't have to include these zeros because they didn't come after a decimal. We only really include zeros when they come after a decimal because that means a level of precision. In this case, these are not very precise, so we don't need to include them. So we can just stop after that 9 or the last non-zero number that we see times 10, and then I would say if I started with a decimal here, how many spaces would I have to go, and in which direction would I have to be moving that decimal in order to create this number. And we see, again, we need to move that decimal to the right, which means this is going to be a positive exponent. And then we say, okay, how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So that would be to the positive 11. And as you see, the larger our positive exponents get, the larger our actual numbers end up being. And then the larger the negative exponent, the smaller the numbers end up being, right? Negative 23 would mean I have 22 zeros in front of something, so that's a super duper small number, and it works the same way, the opposite direction. Writing these numbers in standard notation is a little bit easier because, again, up here in number 5, we have to kind of just imagine what direction we would have to move a decimal if it were to exist after the first non-zero number. Here, you see the first non-zero number and the decimal, and you get told which direction and how many times or spaces you would need to move that decimal to get your number. So in this case, because we have this positive 10, that means I'm going to move the decimal. Since this is positive, I'm moving my decimal to the right. So I start with my 4.53. We're going to erase that decimal once we get our number. But to start, all you have to do is move this decimal to the right 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And effectively, every hump that I've created, I'm going to put a 0 on. Right? And that should give me 8 zeros because of the 10 spaces that I moved. And so now that we've done that, we can just get rid of that, and this is our number represented in standard notation. In this case, we see that this is a negative exponent, which means we're moving the decimal backwards in the negative direction. So we keep all of the non-zero numbers as we see them, and then we take that decimal, we move it backwards 8. Whoops, you gotta love auto correct. 1, 2, 3, 4, 5, 6, 7, 8. And this is where our decimal would end, which means then we fill in all of the humps with zeros until we reach that decimal. And there it is. We keep the decimal that we just created. We moved the other decimal out of the way because it no longer is there. We've officially moved it, and that is our small value here. And last but not least, 2.06 times 10 to the 5th. This is a positive exponent, which means we're moving to the right. 2.06. I'm going to move this to the right 5 spaces. 1, 2, 3, 4, 5. I'm going to end up with 3 more zeros there. Whoa. And that's going to give me number 206,000. All right, so a little bit of review for the scientific notation, and we are good to go there. In this unit, we also did some basic measuring. Being able to measure the graduated cylinder was one of the things that we've done most frequently in class. Remembering that, and it's horrible to read, I know, I'm sorry. But again, this little part right here should be familiar to you. We called this the meniscus. Right, and the meniscus is the portion of the curve that the water or whatever liquid is in our graduated cylinder takes. And so we have to read the bottom of that meniscus at eye level so that we can get our most accurate and precise reading. So we're looking through here and we see that we first, before we can make any measurements, we need to know what increments does our graduated cylinder go up by. And so a way to do that, you could guess and check, or you can pick 2 points on the actual tool itself that you can read a value for that you're given, and you can identify, okay, well, what is what's the difference between there? How many spaces total from here to here? And we notice that that's 5 spaces. And then on top of that, we can figure out, okay, well, how many then spaces do I need to go in order to get there? 1, 2, 3, 4, 5. So what I can do now is I can divide my jump between the numbers that I can read by how many hash marks there are, or spaces there are, until I get to that other one. And what we end up with is, we end up with 1. So this right here is what our hash marks go up by, is 1 milliliter. So you probably could have figured that out just by counting, but again, that's a mathematical way to do that. So now that we know what our increments are, we know effectively that this line right here is 20 milliliters. Well, it's past that, so we keep going. And then this line right here is 21. Well, it's certainly past that, so we can for sure say that this is 21 milliliters, correct? It's not quite up to 22 yet, so we definitely know that we can't start this measurement out with 22. So this last number is going to be an estimate. And this estimate is going to be based off of where our meniscus lies in between those values of 21 and 22. And to me, it looks like it's about halfway. So, the decimal that represents half is 0.5. And so I would say that this could be a very, very not precise, but a good estimate based on the measurement tool that I'm using. And this, again, is an estimate. Now, it wouldn't make sense to say 21.1, because that would mean that the meniscus is just above 20, or 21 in that line. It would also not make sense to make that estimate like 21.8, because that would mean that this meniscus is much closer to 22 than 21. So a good educated guess based on, the eye test, and something that would probably be acceptable would be like 0.4, 0.5, 0.6, something along the lines of that. And so that would be our final measurement. We then did a couple of density calculations just to get the math juice flowing there, and being able to kind of, foreshadow what was to come in terms of the math that we'll end up using throughout, our time together in our class. So once we got that math juice going, we were like, oh, okay, these 3 variable equations are going to be nice to work with, but it's not always going to be that nice, unfortunately. I apologize. But regardless, we do have these triangles that we can use for our 3 variable equations in order to just be better equipped to solve these. It makes it go a little bit quicker. So in this case, we're using the water displacement method to measure the density of this random substance. It's a rock, correct? And so what we know that we have in this equation are 3 variables. We have mass, volume, and density. Well, of course, density is what we're looking for. We have mass, which we're told is 9.3 grams, and then we have 2 volume measurements. Well, that's what water displacement is, right? If you recall, when we do water displacement, we take, because usually rocks aren't nice squares and cubes and spheres where we can't really calculate the volume by measurements. So we have this way of taking a certain amount of water. And so in this case, we're saying that we started with 27.4 milliliters. So there's the 27.4 milliliters of water. And then we take our rock, and I'll make it not a fun shape, or an easy shape, and we put it into there. And what happens is, because the rock has volume, it will take up space within this graduated cylinder. And so once that rock is in the graduated cylinder, because it's taking up space, it's going to cause that water level to rise. And that water level is going to get up to a certain value. In this case, it says 36.5 milliliters. And for our sake, we don't want the volume of the water before and after specifically. We just want those values to be able to identify how much space does the actual rock itself take up. And so water displacement allows us to get these 2 values and just subtract them from each other. So we had 36.5 minus 27.4 to get a volume of just the rock itself. And I'm going to do that here in a calculator really quick, and not pull up the graphing calculator because that's a little much for this. But we should end up with, if what I look at is inputting it correctly, 9.1 milliliters. So what this tells me is that this specific rock takes up 9.1 milliliters, and that's the volume that I'm going to use in my equation. And so now how do we use this triangle? Well, we already know that the density equation is mass divided by volume, but if you just wanted to use the triangle, all you would have to do is cover up what you're trying to find, and it tells you exactly what you need to do with the other two remaining variables that you have. So in this case, density, again, is going to be mass divided by volume, which is 19.3 divided by my 9.1. And then that 19.3 divided by 9.1 is going to give us 2.12. And that unit will be grams per milliliter. All right, so there is our first of a few calculations that we will end up doing. But that is our water displacement. To round this off, we have our accuracy versus precision. And so we're going to do kind of what we did with the physical versus chemical up above. The difference between accuracy and precision: accuracy is the ability to measure, or I would say measure, close to a target value, right? Accuracy is the ability to measure close to a target value, whereas precision, I'll go with the purple and red theme here. Precision is the ability to replicate. It could be either exact replication or very close, within, few degrees, a few decimal places. The ability to replicate measured data. And so we can say very close to, one another. And so what this looked like was we used a target, and I can draw a target here. So, equate it to a dartboard, and we say that if I have, I can have 4 of these flying around. Actually, let's do that. I'm going to duplicate it. Yeah, I love technology sometimes, right? And then you duplicate it. So now we have 4 targets. Oh, did not want to do that. Let's put that back here. Don't know how that happened. A little confused there. All right. So here's our target. Now, ideally, right, in a dartboard, right, we talk about it in terms of measurements, but to visualize this, the goal or the target is the middle, right? And so if you have things that are around the target, well, that means that is you're pretty accurate, right? You got near the target which you were aiming for. However, you would say that these aren't really in the same spot or location. They're kind of spread out around there. So I would say that this is accurate, but not precise, right? So then what would it look like to be precise? Well, of course, maybe I made pretty repeatable marks, right, in the same spot. Well, if I'm to figure out if this is accurate or precise, I would have to look at, okay, where am I in relation to the target? Well, these are not very close to the target, so I would not consider these markings accurate. However, I would consider them precise because they are very, very close to one another. So this is precision. And then we do the same thing for both, right? Here's my markings. I would consider this to be both accurate and precise because the markings, the values that I have are close to each other, and they are also pretty spot on onto the target as well, at what we're trying to get to. And then, of course, you can already picture what it would look like. Oh, well, when is it neither accurate nor precise? And that would be in what looks like this. No accuracy, no precision there. Don't know what happened there, but they're very spread out from each other, and none of them are fairly close to the target value either. So by putting this into perspective with the visual, then we can kind of look and do the same thing with the measurements. And so we see that we have a group of students here. They took some measurements, and those measurements, they look pretty good in terms of repeatability, right? The ability to replicate that. But then they're told that the actual mass, which is the target value, is 50 grams. And so what happens is now we have to say, well, were they close? And we'll give you a threshold, and usually to be close, it really has to be within a few decimal places of that target value. So this is a little further off than that. 2 whole units is quite off. So I would say that the students were not accurate, but they were, and it doesn't make sense to the question, just how I'm saying it, not accurate, or I should say, yeah, let's do not accurate, but they were precise, right? Not accurate, but precise, because they were able to at least get values that were related to one another. All right, so hopefully this is a nice little overview of Unit 1, a nice little quick review, and hopefully this helps. All right, see you in the next video.